Welcome, Hornets. Thank you for joining me today. Today we're going to be going over the worksheet that I gave in class, and this is my final installment of solving for trigonometric functions. This is where we are going to start seeing absolute values, which have multiple solutions based upon the domain, or perhaps not having absolute values because our domain is not excludes any negative possibilities. Now, because we did a portion of this in class, I do recommend that you all go through your basics of ratios and your basic identities. You're also going to want to make sure that you go over, and I'm just going to kind of take my warm-up that I had today, kind of just divide it up so you see the operative portion. This picture right here is going to be fundamental to us as we are trying to solve, because we're always going to be looking for that reference angle, and please be aware reference angle is a measure and therefore an absolute value. So we're always looking between the x-axis and the terminal of our angle. So in the second quadrant, that's right in between here. In the third quadrant, that's down here. In the fourth quadrant, that's here. Notice these are vertical angles from geometry. And as a result, they are all congruent and they are all equal. Okay? So the reference angle is a consistent value around the unit circle in a specific location that allows us or helps us to find the theta we're looking for. In the first quadrant, the theta is the theta prime. In the second quadrant, our angle that's right here is going to have to be pi minus theta prime, whereas in the third quadrant, we're looking at theta equaling to pi plus theta prime. And in the fourth quadrant, we're looking at theta equaling to pi minus theta prime. Now, if we were in degree mode, as we are going to be moving back and forth today, we will be using 180, 180, and 360 instead of 2 pi. So let's go ahead and begin. Once again, keep in mind, I am going to be moving rather quickly as this is a video and I don't want it to be an hour long, which it could very easily be. So we're going to go ahead and we're going to start by adding cosine to both sides so that we have 2 cosine of x plus root 3 equaling 0. I'm now going to solve for my cosine. Cosine of x equals negative root 3 over 2, and I'm now asking myself, when in the first quadrant is cosine root 3 over 2? Well, in degree mode, that's a 30-degree angle, or pi over 6. So I'm looking at 30 degrees. In the fourth, now keep in mind that this is my reference angle, and I know cosine is going to be negative in the second and the third quadrant. So referencing that little piece of paper again, in the second quadrant, we're going to subtract 30 degrees from 180, and our first answer is 150 degrees. And in the third quadrant, we're going to add 30 degrees to 180, and we get 210. In number 2, now you can always work with your difference of squares, and therefore call this 2 sine of theta minus root 3. Once again, I took the square root of all parts. 2 sine theta plus root 3 equals 0. Now this will provide us with the answers of sine of theta equaling root 3 over 2, and that'll happen in the first and second quadrant for sine. And then we have the sine of theta is equal to negative root 3 over 2, and this happens in the third and the fourth. As a result, we now ask, when is sine root 3 over 2 in the first quadrant? This is going to be at a 60-degree angle. In the second quadrant, that's 180 minus 60 degrees is 120 degrees. In the third quadrant, we're looking at 240 degrees, or 180 plus the reference angle 60 degrees. And then the last one is 360 minus 60, which would give me 300 degrees. And those are my solutions. Now, the other way of doing this is by not factoring it, and that's by basically solving sine squared of theta is equal to 3 over 4. And now I'm forced to take the square root on both sides. Notice this is giving me the square root of something squared, which by definition is an absolute value. And I'm now looking at the absolute value for the sine of theta is equal to root 3 over 2. When we drop the absolute value, we have now two possibilities: a negative root 3 over 2, or the sine of theta equals a positive root 3 over 2. Now, one of the advantages of working with our reference angle, or uh, factoring by the difference of squares, is that we'll be able to find both of these positive and negative root 3 over 2's without losing anything. However, if we have this absolute value, that creates problems because we might forget, and when we drop the absolute value, we might forget that negative. And if that's the case, we've lost two of our solutions. At this point, I would then find my reference angle again, where I know that theta prime is 60 degrees in degree mode, and then go through and find all four of my answers: 60 degrees, 120 degrees, 240 degrees, and 300 degrees, respectively. When we are working in radian mode, the only difference is that we're going to make sure we use in terms of pi. Now be aware, one of the most common errors that we have in problems like this is people like to divide by cosine. But when they divide by cosine, they lose a function. And that makes them lose at least one, possibly two, or if there are rotations, multiple solutions. And as a result, they'll lose more and more credit. The way we avoid this is by trying to once again set it equal to 0 as opposed to trying to divide. This will allow me to have a GCF cosine, which I can now factor out. And the cosine of theta times 2 sine of theta gives us a preservation of the function, which means that we will be able to find all of our solutions. When cosine of theta is equal to 0, this happens at pi over 2 and 3 pi over 2 on the unit circle. And when we have the 2 sine of theta minus 1 equaling 0, our sine of theta is going to equal 1/2. And we know that this is going to occur in a 30-degree reference angle, or when our radian is pi over 6. So our answers are in the first quadrant and the second quadrant. That's going to give me pi over 6. And then I have 5 pi over 6. Once again, pi minus the reference angle. These then become our solutions, which we can arrange from least to greatest, greatest to least, or however your teacher might like you to represent them. For me, I personally like to have my students just list the ones that we have, and if they want, they can put it in a solution set. This brings us to number 4 here, and notice this is a quadratic. And then if it's a quadratic, I'm going to use my dummy variable u, and therefore u will equal the sine of x. Substituting u with the sine of x gives me 2u squared minus 3u plus 1, and I can factor this easily into 2u minus 1, and u minus 1 equaling 0. I then back substitute to get 2 sine of x minus 1 times sine of x minus 1 equaling 0. This gives me 2 sine of x minus 1 equaling 0, so that sine of x is equal 1/2. And once again, we saw that in the previous problem, so we already know that this would have to be pi over 6 in the first quadrant and 5 pi over 6 in the second. Then finding when is sine of x equal to 1. Now this is a quadrantal, that means there's only one solution. It is sitting on an axis, and this occurs at pi over 2. My solutions are therefore pi over 6, 5 pi over 6, and pi over 2. Now, sometimes we have to become a little bit more creative, and there's no way around the fact that we're going to have to use some of our identities. As a result, I'm going to make sure that I recall that the secant squared of x is equal to 1 plus tangent squared x. Now, this is not the only identity that I can use. In our previous section, we worked with verifying identities and we saw a boatload of them. And a lot of them, and they were different things, being they secant, being them equal to, whatever it might be. So if you come up with your own identity, as long as it is valid, you will come out with the exact same answers that we do. For example, someone might want to change the tangent into a secant and work with secants as opposed to me, where I'm working with tangents. As a result, when I plug this in, I end up with 3, 1 plus tangent squared of x minus 2 tangent squared of x minus 4 equaling 0. I distribute the 3, and now I can add like terms. Now once I do this, I end up getting my tangent of x, tangent squared x, minus 1 equals 0. And now I have to decide, am I going to add 1 and take the square root, in which case I have the absolute value, have to rewrite it twice, once with a negative 1, once with a positive 1. Or am I going to factor it and thereby work with the difference of squares, giving me the tangent of x plus 1 times the tangent of x minus 1 equaling 0. That means that tangent of x would have to equal negative 1, and the tangent of x would have to be a positive 1. We know that tangent of x in the first quadrant has a reference angle in radians of pi over 4. That's where sine and cosine are equal. And in the second and fourth quadrant, we know that our tangent is going to be negative. So let's just go ahead and do first and fourth, and then go to our second and third. Notice, I'm able to do this quickly because I know my reference angles, I know my trigonometric ratios for the various functions. I know my identities. Without that, this becomes very, very difficult. And no matter how many times you see it, if you do not learn your identities, you do not learn your ratios, it's not going to matter. Now the second option is right here, where I take my tangent squared of x equaling 1. I take the square root. I then get the absolute value for the tangent of x equals 1. And now when I drop it, I have 2. Negative 1 or tangent of x is equal to positive 1. Please do not use the plus minus symbol. That will cause issues, and I would rather not have you go there. Once I've got this, I now solve for them, just like we did before, and life is grand. Number 6, being creative. I know that if I can figure out a cosine squared, I can turn it into sines. So that's what I'm going to do. I'm going to square both sides. Now this requires us to just have practice in our work. The more you practice, the easier it's going to recognize when to square things versus when to multiply by a conjugate pair versus when to do some type of other substitution. I can now work with my cosine squared is of theta is going to be equal to 1 minus sine squared of theta, so that the sine squared of theta plus 2 sine of theta plus 1 is going to now equal 1 minus sine squared of theta. When I subtract 1 from both sides, they cancel. When I add sine squared to both sides, I get 2 sine squared theta plus 2 sine theta equaling 0. I can now factor out the 2. I can factor out the sine of theta, and I'm left with the sine of theta plus 1 equals 0. So when is sine of theta equal to 0? Notice 2 can never be 0, and I don't work with that. But when sine is 0, this occurs at 0 pi and pi. Then I ask, when is sine of theta plus 1 equal to 0? And this gives me when is the sine of theta equal to negative 1. Sine is only negative 1 at 3 pi over 2. I now put them in my solution set. arrange them in the specific order that your teacher may want, and move on to the next question. We're now in degree mode. We're finding multiple angles, and we're going to do the exact same thing that we've done in the past. We're going to call it sine of 2x equals root 3 over 2, and I'm going to use a dummy variable and let alpha equal 2x. This then gives me the sine of alpha equals root 3 over 2, and I can now identify that this will occur in the first and the second quadrant. The alpha in the first degree giving me root 3 over 2 is a 60-degree angle, and in the second quadrant I'm looking at 180 minus 60 for 120 degrees. Now we're going to have to take these two solutions that we found in terms of alpha and now set them in terms of 2x. We have to remember that we're going to add 360 degrees K. We're going to have this happen twice. So 2x equals 120 degrees plus 360 degrees K. We're going to then divide. We're going to divide everything by 2. Notice we now have x equals 30 degrees plus 180 degrees times k. Well, we're going to let k equal 0 and k equals 1. Here we're looking at x equals 60 degrees plus 180 degrees times k. When k equals 0, we have 30 degrees for the first one, and we have 60 degrees for the second. When we let k equal 1, we have 210 degrees for the first, and we have 240 degrees for the second. And these constitute my solutions, which I now put in a solution set. Sometimes we are forced to use our calculator, and when we use our calculator, hang on just one moment as I pause this. Thank you for giving me that opportunity to go and get a calculator. Please recognize that we are going to be in degree mode, and to find degree mode, we hit mode, so on, mode, and we go down and we put it on degrees, so the degrees is in the black box. We're now able to solve this. We're going to use the dummy variable u equaling the tangent of theta, so that I have 4u squared plus 5u, and notice I'm going to move this 6 over so that it's minus 6 equals 0. I'm now going to attempt to factor. So I'm just going to break this down. It's easiest to look at the 3 and the 2. I know that I'm going to then have a u and a u, and I want to end up with an 8. So I'm going to put a 4 here, and I'm going to subtract the 3. So this is going to be a plus and a minus. Notice I now have minus 3u, positive 8u, and I end up with the sum of positive 5u. Now I'm going to put the tangent back in. Tangent of theta plus 2 has to equal 0. For tangent of theta minus 3 has to equal 0. Therefore, the tangent of theta is going to equal a negative 2. Now remember, we know that we're about to get the opposite of our reference angle. For this one, tangent of theta is going to be 3/4. Once again, non-standard angle, thus the calculator. Now we have to remind ourselves that when we are working with a tangent with the negative, we want to get a positive result. In order to get a positive result, we're always going to add pi. See, we're going to get either an answer here, or we get an answer here. If we get an answer in this one, we add pi to find it. If we're using this one, and I'll use a dotted line to distinguish them, I add pi to get that straight angle. So for this one, the tangent of theta, when I work with the arc tangent, is going to give me a solution. And I will find the second by adding 180 degrees to get that straight angle. In radians, I would add pi. In the second one, I'm going to use, and notice I'm going to get the negative theta prime, and therefore I'm going to add pi once, or 180 degrees once, and then 180 degrees a second time. Here we go. Second function, Second function tangent in degree mode of -2 is giving me -63. Now that means that my theta prime is 63.4349 degrees. Well, if that's my reference angle, I'm going to simply take the negative and add pi, or 180. I end up getting my first solution, theta 1. Theta 1 is then approximately 116.5651 degrees. I'm now going to add 180 again. My second solution, theta 2, is going to be 296.5651 degrees. I'm now going to go to my tangent of theta equals 3/4. This is going to be my third solution. So I have second function tangent, 3 divided by 4. We know it will be the reference angle, and so the reference angle here is the first solution in the first quadrant, which would be 36.8699 degrees. And that will be my reference angle. Again, I did round. We're now going to find the second answer for this one, which will be the fourth overall answer, and I'm going to add 180 degrees to it. I end up getting 216.8699 degrees. And I now have all 4 solutions. They are non-standard, between 0 and 360. Keep in mind, if I had something like 720, I would keep adding 180 degrees until my values exceed the domain that we are seeking. Now the next worksheet is asking us to continue to work with this. But notice they do not give me a domain. They ask me to find all possible solutions. So I'm going to use my dummy variable, u equals the sine of theta, so that I have 2u plus u minus 1 equals 0. I therefore can factor, don't forget your squared, Mr. Lamb, 2u, u, 1, and 1. In order to have a positive u, I need 1 to be positive, and the negative will have to go here, and it's set equal to 0. We're now able to back substitute. 2 sine of theta minus 1 equals 0, and sine of theta plus 1 equals 0. I'm now going to solve, so I end up with sine of theta is equal to 1/2. Now, we know in degree mode, sine is 1/2 at a 30-degree angle. So I have 30 degrees plus 360 degrees times k, where k is an element in my unit circle, or in integer, excuse me. There's my first group of all solutions. I'm now going to do it again. This time, I have an answer in the second quadrant, and that's 150 degrees plus 360 degrees k, such that k is an element of the integer set. We now go to the sine of theta equals -1. Well, the sine of theta equals -1 at 270 degrees. So I'm going to have 270 degrees plus 360 degrees k, where k is an element of the integer set. And I now have all of my solutions. Number 10. If I start by dividing both sides by 5, you'll notice that I'm really looking at the sine of theta plus 1 equals 1. And therefore I have the sine of theta equaling 0. As a result, I'm asking, when will this occur? And in degree mode, I have 0 degrees plus 360 degrees k. Finding the second one, where else is it 0? I'm looking at 180 degrees plus 360 degrees k. Now, some people are going to realize that if I just keep adding 180, it's the same thing, and all I'm doing is going back and forth. So if here's my axis, I'm going from this side to this side, then back, and back and back and back. So I can write a unified theory or unified formula, which would be 0 degrees plus 180 degrees times k, very similar to our tangent. And this is where k is an element of the integer set. Now, here are my two solutions, and here is all of the solutions using a single formula. Working in number 11. Now, when I'm working with number 11, I'm going to want to try my best to make sure that I bring things over. So I'm going to subtract a tangent, and that's going to give me 6 tangent theta, and it equals 3 root 3. Dividing both sides by 6, I get the tangent of theta is root 3 over 2. Now, let's just make sure 6, up. So I subtract 1, I get 6. I divide 6 times 3, factor out the 3. Alrighty, here we go. I'm going to have to use my calculator for this. So I'm going to be doing the second function of tangent is root 3 divided by 2. And my first answer in degree mode is 40.8934 degrees. And we know that this is going to happen in the third quadrant. So I'm going to add 180 degrees times k, where k is an element of the integer set. This will now give me all coterminals, as I have that 40-degree angle like this, and I keep going back and forth and back and forth. Number 12. Factor out the cosine just like we did today earlier. And let me get my theta in here. And you'll notice I'm left with 2 sine of theta plus 1 equaling 0. Cosine of theta has to equal 0 at pi over 2 and 3 pi over 2. And if we were to continue, I would then just add another 2 to be 5 pi over 2, 7 pi over 2, and this continues indefinitely. Well, we want a single formula, and you'll notice each time I'm adding pi. In degrees, we're looking at 90 degrees, and then this one would be 270 degrees, and then we would have 360 plus 90 would be 400, let's see, 360, 470, 450 degrees. And this continues. So what I want to do is I want to have theta is equal to 90 degrees plus 180 degrees times k, where k is an element of the integer set. And this will find all of them for this first cosine of theta equals 0. The second one gives me the sine of theta equals a negative 1/2. And we know that this is happening in the third and fourth quadrant. The reference angle is pi over 6. So I have 7 pi over 6, and I have 11 pi over 6. Each of these is going to have to be separated, and if I need to put it into degree mode, I'm looking at 180 plus 30 is 210 degrees, and 360 minus 30 degrees is going to give me 330 degrees. Putting them together, theta is equal to 210 degrees plus 360 degrees k, such that k is an element of the integer set. And finally, our last one, all of the solutions, we have 330 degrees plus 360 degrees k, such that k is an element of the integer set. These are now all of our solutions in terms of degrees. Now, radians is simply the same thing. I'm just going to solve in radians, and I'm going to make sure that I now add 2 pi k or pi k. So I have cosine of theta equals 1/2. That's going to be in the first quadrant, pi over 3. That's my reference angle, which means that I now have pi over 3 plus 306, plus pi k, 2 pi k. Make sure I put my period in. 2 pi k, where k is an element of the integer set. There's my first group of thetas. Now, I know this is also happening in the fourth quadrant where cosine is positive, and that would give me, with I have pi over 3, I'm looking at 5 pi over 3, 2 pi minus theta prime. I'm then adding 2 pi k, such that k is an element of the integer set. Now, I personally find that finding my multiple solutions or all solutions in terms of pi or radians is more easy to work with than dealing with degrees. Once again, we all have our little areas where we continue to struggle and work. It is not different for anyone, even myself. I may have been doing this for 30 years, possibly as long as 40. I don't want to tell you. However, that doesn't matter. We all make mistakes. That's why I always tell everybody to try to be kind to each other, because we can do things without recognizing it. Those microaggressions that we've been talking about in class. I'm going to go ahead and I'm going to subtract 2 sine of theta. I'm going to subtract a 1, or in this case, I can add a 1. I end up with 2 sine of theta, and it's going to equal 2, which means that the sine of theta is going to equal 1. Sine of theta is going to equal 1 only at pi over 2. So theta equals pi over 2 plus 2 pi k, such that k is an element of the integer set. Now you'll notice we're going to keep doing this over and over and again. So in the next part of this, we're going to be just turning the page, and you'll notice that we have this cosecant here, and if I try to factor out the cosecant, I have cosecant of theta is secant of theta plus root 2 equals 0. I'm now looking at the cosecant of theta equaling 0. And we have the secant of theta is equal to negative root 2. Now, when we talk about the cosecant, it's important to remember that our cosecant, as well as our secant, have a range that must be greater than 1 or less than negative 1. And you'll notice in between negative 1 and 1, the cosecant and the secant cannot work, which means that this portion right here is a no solution. It's an extraneous value and something that we have to account for. Don't just ignore it, please. If you ignore it and you don't put no solution for that, I'm going to have to take off credit, and that could get you a little bit frustrated. I'm now going to attempt to find when my secant is root 2. This is my reference angle. We know that cosine is root 2 over 2 as a radian. I believe I am doing radian mode, and that was at pi over 4. So I now know my reference angle is pi over 4, and in order to have cosine a negative, that's going to happen in the second and the third quadrant. Once again, we're going to be finding all of our possibilities. So in our second quadrant, we're looking at theta is going to be equal to 3 pi over 4, and we're going to add 2 pi k, such that k is an element of the integer set. And then we're going to go to the third quadrant, and theta will have to equal 5 pi over 4 plus 2 pi k, such that k is an element of the integer set. Number 16 here, I'm going to use my Pythagorean identity of 1 minus sine squared theta is equal to cosine squared theta, and that's going to allow me to substitute. Now I will also point out that I could use my alternate view of sine squared theta is equal to 1 minus cosine squared theta. However, that could be a little bit more difficult, and I'd have to subtract 1 and regroup. So I could say that the negative of 1 minus cosine squared theta plus sine of theta, or x, excuse me, let's use the x here, is one option, and it would be equal to 0. Now I could substitute and have negative sine squared of our x plus sine x equaling 0. I can move things around so that 0 equals sine squared x minus sine of x, and from that I could factor out the sine of x. That's one option, and I could find my solutions that way. Or I could do a direct substitution and have 1 minus sine squared x plus sine of x equaling 1. The 1's have to cancel. You'll notice I'm right back where I was, where I would rearrange everything and start solving again. Once I have it set up, I can then find when is sine of x equal to 0 and when is sine of x minus 1 equal to 0, so that when is the sine of x equaling 1. This has to be at pi over 2. This is 0 pi and pi. Notice this is separated by 180 degrees, so I'm going to have 0 pi plus pi k, such that k is an element of the integer set, and that will now account for all of my thetas there for this piece. And then this one would be theta is equal to pi over 2 plus 2 pi k, such that k is an element of the integer set. Now I have to use 2 pi so that I can get that coterminal. So if I'm here, I have to go all the way around to get it again. That's adding the 2 pi k. Whereas if I'm looking at this one, and my zeros occur here and here, they form a straight angle, and that's just adding pi. Solve each trigonometric function in the interval from 0 to 360. We're now back to where we were. We have to decide, am I going to move things around and square both sides? Am I working with multiple angles? What will it have to be? Now, the answer key is provided in the Google Classroom for each of these, and I recommend that you give them a try on your own. Thank you very much, Hornets. This is what I have for you today, and it's my hope that this was helpful to you. If it was, please click like. If you have suggestions, please feel free to offer me suggestions. Thank you very much, and I hope you have a wonderful evening, and I hope things go well for you. Please remember, it is easy to be mean, so please try hard to be nice to people. Think about what you say. Think about how you say it. We can be mean with a gesture, with silence, with a word, with an action, with an inaction. All righty. Take care, be well, be safe. Bye-bye now.